All right. So this presentation, I'm going to kind of springboard off of, and thank you, John, for all of the background on this. This presentation is based on recent tech note that 551 committee published that dealt with some of the things that John talked about, this modulus eruption, the effective moment of inertia, and what happens and can go wrong if you start altering those and deviating from this. So the tech note, that's an image of the tech note. It's available now from ACI, and then also some of the examples that I have can be found in the design guide. So outline, we'll talk about application and design methods just briefly. History, John has covered most of that. If you download these, I think these slides will be available, so if you download them, I left some of that information in there, but we'll skip through it pretty quickly here and get back on time. But John gave it a lot more better treatment than even what I had here, so great. We'll talk about the pitfalls, 1, 2, and 3, modulus eruption, effective moment of inertia. We'll look at the examples and see where things kind of can take the wrong turn here. And then we'll talk about iteration versus direct calculation briefly. Yeah. So slender wall design provisions, these are provisions that are intended to apply to single-story structures. We're talking about the out-of-plane design of these panels for axial load and lateral loads. We're not talking about the in-plane design of these. Consideration of the second order effects is significant. All right, and then we're not talking about multi-story buildings related with this. So some additional pictures, various tilt-up buildings that are very common. Most of these are one-story structures. You can sometimes really have some upper windows, but they're still usually one-story, or may have a minor mezzanine. So these are the type of buildings we're talking about. So common design practices, hand calculations, spreadsheets, in-house calculations, and then software packages. Kind of all three of those. And I won't take a survey, but you probably have seen some version of all of these. And you know, I know in our office we use some spreadsheets that we've developed. Hand calculations, often the first few times an engineer goes through this, encourage them to get out the pencil and do some of these calculations. It can be done all by hand, and it's good to understand what the software uses. But then there are software packages that facilitate design. And I think what we have seen and heard and experiences from people are where a lot of concern comes from is the black box approach. And there are software packages. Some of what I'm going to show you in some design examples grew out of, actually, for me, it was a peer review project that we did, and we started looking at design results and saying, wow, how did this come to be? How did they get to this answer? And looking at what the software programs were facilitating, and then starting to check those things and realizing that this is really getting some designs that really gave us a lot of concern. And so if you're using software packages, really want to underscore the importance of looking into what is being done in that software. Codes, so ACI 318.19, the references in here. There is, when we talk about these slender wall provisions, we're typically talking about section 11.8 in 318. 318, chapter 11 is the wall design provisions, and it actually lets you use several methods. 11.8 is an alternate procedure. So that begs the question, alternate to what? So there is a primary procedure for walls that's allowed, and it's in 11.4.1.3, and it references and says if you're going to use, you can use this, and you can go use the general, what I would call the general second order provisions of ACI, which are in chapter 6. If you're doing these tall tilt-up buildings, though, you're going to find that this can give you some different results. And I would recommend against using those provisions for these types of walls. They weren't developed for that. This is really beyond the scope of what this presentation is, but I really use a lot of caution and recommend against doing that unless you really have eyes wide open. So, and then the 551 has a tilt-up design guide with a lot of information. So the ACI, the provisions in 11.8 break down, and we'll look briefly here in just a second at the actual provisions as they're written. But there's two sections to those provisions. One is strength-based design, one is serviceability, okay? A lot of what John presented and showed you is on the serviceability side and predicting how that panel is going to deflect, looking at, you're going to get some permanent deformations if you get too much of it. What I want to look at and really focus on more here is going to be the strength side of that equation. As designers of panels and buildings, our first responsibility is to make sure that we have a safe structure. And then we can worry about serviceability. But we've got to make sure it's strength, that the strength is there and that it's safe, and that we've got behaviors that we can predict and that we know how these things are going to fail. We don't want, especially in concrete, we don't want sudden failures, right? We want that ductile response, that we know how it's going to behave and control. And so the strength design provisions want to provide safety. They're based on a cracked section. It's how the code is written, and for good reason. We're going to find our maximum, our factored moments from iteration or direct calculation is allowed. We've got to use a cracked moment of inertia, and we want that ductile behavior versus serviceability, where we're looking at function, and we're trying to be as accurate as we can in predicting what the actual in-service deflections are going to be. We're not looking at that extreme event for safety. We're trying to be accurate in predicting them. So the bilinear curve John talked about, here are the provisions. So this is strength design, and you can find your moments here. Let's see, this has, so here's moment equation. So we've got an applied moment and a second order moment. And then this gives you, by iteration, you can calculate this, okay? So moment based on your deflections. Deflections are based on moment, there's your iteration, okay? So that's, the second part of this though, comes down and it gives you by direct calculation, and you can use this equation to do this. And I'll show you in a minute, was these should be exactly the same, okay? Regardless of what you use, as long as you use a cracked moment of inertia for your calculation. And that cracked moment of inertia is right up here, and here is the equation for it that they're asked to use. The second part of the provisions in here are service deflection calculations. This is the formulation that's in there. It's the bilinear curve. The first portion, it's the elastic and the steep curve, and then as it flattens out, would be the second portion down here. Okay? And then the variables that go into there, and as John noted, that has to be done. You have to do iterations to get the accurate result here. So history, the testing, you had nicer photos, John, color and everything. Mm. So, but if you want this information, I think that SEOC, the Structural Engineers Association of California, actually still sells both of these publications. And if you're interested, here's the provisions in the 97 UBC. And we talked about this modulus eruption, the 5 F prime C versus 7.5 F prime C. Okay. And then the equations that were for I effective that were used, the Branson's equation was put in. So let's look first at this first one here. Is the modulus eruption. Our curve, and where that panel cracks and the curve takes off. Okay, and as John noted, the 2/3 factors in there to scale. ACI's favored 7.5 root versus the 5 root of prime C, and so the 2/3 factor takes care of that. So now let's look at the next one here on the I effective. We'll get to an example here, but Here's the provisions that were in the 97 UBC. And when this was adopted into the 99, ACI took these provisions. This is as the uniform, the IBC, so the International Building Code, was coming into effect in 2000. And so ACI 31899 adopted these provisions, and when they did that, they incorporated the I effective from Branson's equation, put that in, and the results that we get out of that. And the comparison here with Bishop. So I'm going to skip through that here. So in the midst of all of this, and we went from, it wasn't until I think, so it was the ACI 31899 up to 31805 that had the I effective in there. And during this time, as engineers became aware of it, they said, you know, we don't want to fall into the trap of this curve that's misapplying this. Let's find something better that works. And so there were some engineers who found Bishop's equation, and they said, let's put this in. This is going to be a great way to get to calculate our panels. The problem is that they took Bishop's equation and they put it into here. This isn't the serviceability side. So Bishop's equation does a very nice job of predicting this bilinear curve. But that's great on if we wanted to try and apply that on a serviceability side. If we want to do that on strength, now we're dealing with safety. Okay? And the capacity of our panels. So if we take this I effective and we now put it in down here for our I crack, we're now putting this into strength design provisions. Okay, so here's Branson's equation, follows pretty nicely, except that we want serviceability. So let's look at what happens when we do this. So our panel design model, when we calculate per panel, we calculate our primary moments here. We've got the WL squared over 8 from a lateral pressure. We've got our axial load and maybe some eccentricity on it. Those are our primary moment here. And this is out of the design guide from 551 for panels. So, and then we've got the secondary moment. And this is the part that we get particularly worried about if we're using the wrong predictor for what this deflection is. So the basic tenet of concrete, when we're dealing with strength design, is that we're going to ignore the tensile capacity of concrete, because that's that sudden rupture that we can't necessarily control, right? So we're going to ignore the capacity of concrete in tension, and we're going to use the steel for that. That's our ductile way of controlling that. And so this is the basic kind of tenet that's in ACI here. So tensile strength of concrete shall be neglected in flexural and axial strength calculations. Notice we're saying strength, not serviceability here. Strength. Okay. So strength of concrete and tension, however, is important in evaluating cracking and deflections at service loads. Again, when we're trying to be very accurate, we want to take all those factors into account. So when we look at strength requirements, here's our basic Whitney stress block kind of formulation. This is what we're going to brace the strength of the section off of. Okay, and the equations that you're probably familiar with if you're designing these things. It's a tension-controlled section. We're ignoring the capacity of concrete in tension. We're looking at and doing our transform section here with our steel, with the tension side, concrete in its compression side. Okay, and this model that we're going to use for the strength capacity of our concrete is based on the assumption that it's a cracked section all the way through. Right? So those are the general equations for calculating the parameters including I cracked. The cracked section modulus comes from the same model, same diagram. That's where we get it. So the beam analogy, beam bends, the cracks. In this case, we've got an axial load. We're just turning this up, down. All right, so examples. Here's an example problem from the design guide. Let's look at it quickly. I know lots of equations, so we'll go quickly through these, and I'll point out here a couple of things that we see, what the results that you can get. So if we calculate, so we've got a panel, 6 1/4 inch panel. We're putting some joist loads on it, 7.2 kips of dead load, live load of 7.5 kips. We've got 16 number 6 bars and a 15 foot wide panel. So we calculate our factored axial load. We calculate the weight of concrete that's applied, our total applied factor load, our area of steel, and an effective area of steel, so we get some benefit from the compression there. Notice with the nomenclatures here, so U is factored load. A, this is kind of what's used in the guide. A is the applied load of the critical cross section, which happens to be the midsection, and then a factored applied load of the critical section. I think the design guide also uses use of M, which is a factored load at mid height, and I think sometimes these nomenclature gets a little bit confusing, but we'll ignore this one in here. So strength design. So these are the strength design equations that come out of this. Calculate our stiffness of the panel based on a crack moment. We get 61.2 kips. Kip feet a moment, we get a deflection of 10 inches, which is large, but again, this is the extreme event. Okay, this is the outside bounds for the strength design. So let's do the same equations with Bischoff's method. And this is, again, there's software out there that facilitates this, and you can push the little button and you can get these kind of results. And so you get I effective. When you calculate this is from Bischoff. Nothing wrong with Bischoff's equation here, but notice that we get an I effective and we get a negative value. That ought to be a little bit of a red flag, but my experience, I've seen you move on from these calculations because you go, well, my cracking moment and my factored moment, my cracking moment's bigger than my factored moment, which means that I'm on that elastic vertical part of the curve, right? So let's not get too worried about this. That just must mean that we need to use I gross, okay? So I plug those values in, and now I've got a stiffness here, and I get a moment of 26.3 kip feet. So now I've reduced my moment by more than 2 for my design moments. And I've done that because I based my second order effects on now the gross section properties. Okay, and my deflection is way down. So here's a comparison. If I plug in those values into the strength equation, and you can see here 61 kips versus 26 kips. Okay, you're going to get a lot less steel in the panel, but the challenge is that you're now designing on this elastic part of the curve. What happens when your panel suddenly cracks? Whether it's an overstrength event, whether it's during lifting, maybe the panel has some impact. If you're designing down here on this vertical part of the curve, the panel gets cracked, you're not going to have the steel necessarily to arrest this panel from getting excessive deflections and sort of crushing. Fortunately, the test results are that these panels do behave pretty ductily, and they can take a lot of deflection. But our equations are clearly saying this is going to be in an area of design you don't want to be. So one more example, we'll go through quickly here. This is a panel. So this is a girder load put on a panel, 8-foot wide panel, number 5 bars at 16 inches on center. So factored load 73 kips, applied concrete weight, get a total applied load 85 7 kips area of steel, effective area of steel, because we've got lots of axial loads that goes up. But let's design this panel using Bischoff's method. Let's put in the I effective, okay, or instead of I crack in here. So we're going to do this. So here's our crack moment, our gross moment, our cracking moment. Here's our primary moment on the panel, 14.8 kips. Okay. Here's our I effective. Again, we're getting a negative I effective, which tells us we're on that elastic part of the curve. Okay. No need to stop there. We'll just use I gross. Put that in. Here's our factored moment now, 17.8 kips. So on the previous example, the total moment that included the second order effects was almost 2.5 times the primary moment. Here I had a primary moment of about 14 kips, and now I got a total moment including the delta 17.8, which makes sense because if I'm only designing for that very vertical part of the curve, it's not going to have much effect on the panel. But let's look at this and compare it. If we go back and did it the correct way and we use the cracking moment, here's our, well, in this case, we got a negative moment now. So now here's our moment, and now we've got a negative moment of minus 15.7 on this panel. Okay. So there ought to be some red flags at this point if you're doing design this way. If you're using software and it's doing something like this, you're not going to see it because it's, you know, it's in the black box. Negative deflection. Here's our comparison. Here's ACI's provisions in 11.8. Negative moment. Here's our total moment. So this gives us some indications of what's going on, and that's here. This is from the design guide. Is that if you don't have enough steel in the panel, you get this asymptote that occurs at this balance point, and you want to be designing out here. But you could inadvertently be down in here, in this section, and that's why we're getting a negative in the way those equations work. Okay. If we were to design this panel using the ACI methods and actually get the calculation, we'd get a moment of 61 kip feet would be actually where we would come out with the design moment, not 17. Okay, and our steel, instead of being number 5 in the center of the panel with 16 inches on center, we have number 5s each face at 13 on center. This was the equivalence. Okay, so again, this example with the girder I took from it was a peer review, and I watched people design and put this into building and service, and then try to argue that this was okay. They said, yeah, I think you need to go back. Now you need some columns and some strong backs on those panels. So one last quick note, the direct method, I heard this, another pitfall is that people say, well, my calculations are correct because I'm going to read instead of using a direct design, the provision that's allowed in the strength, those strength provisions. It's in the design guide, but if you go through it, they're exactly identical. If you're correctly using the crack moment of inertia, it's a moment magnifier method. The derivations in here, and it's in the slides, and it directly compares, and you'll get an exact solution. It's the same. So very quickly summarizing here, the pitfalls. Make sure you know which modulus or rupture you're using, and know what the software is doing. And it's tricky too, because if the software gives you a choice between 5 and 7.5, you want to make sure what you don't know necessarily is the black box using the 2/3 factor to choose the 7.5. So you want to know which it's doing, and you don't want to use 5 and 2/3 end up using 2/3 of 5, right? So you want to know what you're doing. Effective moment of inertia, serviceability only if you're going to consider that, but it's not for strength design. The direct calculation. My recommendations here: calculate if you want to check what's going on, calculate your moment and your deflection by hand using iCrack, do it for a panel. Compare it to software, a spreadsheet. This can happen even with spreadsheets. If they've been around in the office for a long time, you know, how were those done? Maybe the primary author, I know in our office, the author that wrote it, you know, that wrote the first program 25, 30 years ago, you know, it's been moved on long ago. And so, you know, it's good to go back and check those things. If you know the values that they're using, you can back calculate an I and compare it to iCrack or iGross and see what you're getting and see what it's doing. Check the software with known panel designs that follow ACIs. So, yeah, calculation. So, slides have some of the reference material. The TCA book is also another good resource for engineering tilt-up designs. There's some references in here.
Thanks.